the change is something because I getting know what you are, who you are. I mean, so I wanted to make some kind of the level and the content you wanted to have. So that's why I'm changing. He wanted to have revised one because it's different from the previous. Okay, today I have 2 lectures, and I'll make it in series. Okay, at a time. It will take about 2 hours or less. Okay? Today, so I'll talk about the manufacturing technique, the oriented. So manufacturing technique for composite. So among many techniques, I will talk about 3 crucial things: filament winding and vacuum-assisted manufacturing process, and automated tape laying. So those kind of things, right? So, so this is a manufacturing technique for composite. The filament winding is one of the oldest one, but most the valuable thing even these days. So it is well automated now, but very expensive. So most of combustion material machines, related machines, are very expensive. But this one is very well established and well developed now. The filament winding is we say cutting edge technique because it's fully automated, and so it's now it's revolutionizing the production, the high strength, lightweight structure, especially for aircraft and the sports goods. So this is just some of the sample or pictures in real industry. So you can see so this is the machine, empty machine, and it has barrels. Okay? This is winded around the cylinder. And this kind of, this is in the process, okay? Not fully winding yet. And this is also. So this kind of winding machine is very useful these days and well advanced. To use those kind of winding machine, so firstly, fiber preparation is the starting point. In fiber preparation, usually it's, as you see, it uses continuous fiber, not the chopped fiber or something like that. So continuous fiber implemented connected with resin, and it's wound onto rotating machine, rotating a mandrel. Mandrel is rotating all the way, and winding process, and so its fiber is placed on the mandrel, and the process is controlled by computer for accuracy. So it's winding angle and winding speed and the tension in the fiber. Is everything should be very carefully controlled. So it is very difficult manually, because in the case the constant tension is not possible. It means in the real use, in the case, you will get unwanted residual stress. So it's very the unwanted situation. So, so after winding process, curing is needed. Curing is in the oven or in the that curing process means heat treated. Okay? So during heat treatment, this wound the product is solidified. So it is a final product stage. So key components of a filament winding. So in the machine, so fiber delivery system is needed, resin bath needed, mandrel needed, carriage needed. So instantly you can understand already. So why the delivery system, what kind of function must be done by that system, and the resin bath also that is needed to impregnate the fibers before wounding, and the mandrel is just a base to be wound, and carriage is because that machine head must move through by using carriage. Okay, and the filament winding pattern is it is three the typical patterns are used. For cylindrical mandrel, the helical wounding, because it has some fixed angle or winding is needed. So helical winding or the hoop winding is like the waist belt. So hoop winding case, and if it is not cylindrical shape, it's a spherical shape, something like that, in the case of polar winding technique is needed. So those can be controlled from the control panel. And material selection for filament winding, usually we typically use three different ones. It is those are not limited for use, but this is very the typical ones: the glass fiber, carbon fiber, and aramid fiber. So, I have not seen this fiber from my experience, but I can find this one from the documentation. So it is some of plastic resin type and corrosion resistant types application. Yes. But what I seen so far is that these three different kinds of fiber type I have. So. Also, the pressure vessel is most common use for filament winding process, because the pressure vessel is mostly cylindrical shape, okay? And the end cap is hemisphere. That means the filament winding is very useful for those structure shape, and it's the filament, the fiber tension should be very uniform, very uniform, to keep right circle or such like that, because the inside the pressure should be borne. And carbon type is usually used for aerospace components, and the resin type is polyester is needed. So epoxy, polyester, or vinyl ester, those kind of things match with aramid, carbon, glass, respectively. Right? So the reason the aramid is used for automotive drive shaft, because it is very strong to impact. So it is highly impact resistant. So aramid fiber is used for the automotive drive shaft. And the process parameters and the optimization. So usually we can control temperature and the winding speed and the fiber tension and the winding angle, as you expect. Okay? And the quality control and inspection is needed. So once so you're operating the machine, then from the final product, you should visual inspection first, and non-destructive testing is mandatorily engaged. And there's ultrasonic X-ray inspection is used to be to find internal flows, if any, and ensure structural integrity without damaging the part. It must be checked. And technical mechanical testing is also engaged. The strength stiffness test on samples. So that means the whole, the finally wounded one cannot be mechanical tested in the case it is used. So when they manufacture the winding product, so every lot they make different the test specimens based on the same combinations. So every time they check the mechanical testing result is a successful the mechanical properties displayed on that they should check that. And the dimensional analysis means the geometry part. It must be precisely manufactured in dimensions, because it should be assembled with other parts. And mostly this expensive structure used for aerospace engineering. So it's very large scale, and its dimension must be very tightly accurate. And application of filament wound composites is aerospace, sports equipment, energy, and the infrastructure. So if it is tubular type body, in the case it will be chosen for filament wound composite type. Okay? And except that kind of filament winding method, there are other techniques to manufacture FRP composite, FRP fiber reinforced polymers, or fiber reinforced plastics, you can say like that. And the typically we can say the hand layup method and the vacuum assisted resin infusion, we say is a VARI. And the resin transfer molding is RTM, and the compression molding method. Those kind of in this category, SMC is usually used. So firstly, let's see, the hand layer method is very simple one, very the old method, very the directly understandable one, right? So this any kinds of fiber mat is prepared, and this the gray one, dark gray one is mold. Is mold on the mold. The resin film and the gel coat is adopted, and so you stack the carbon, in this case carbon fiber mat, or other case glass mat, any kinds of mat prepared is stacked as desired. Okay? And after stacking, the hand roller, by using hand roller, you load the pressure the evenly along the surface of stacked the mat. This is very simply understood, but RTM process is a little bit complicated, but this is also one of very traditional one these days. Okay? So because these days RTM itself is not widely used, because it's that traditional method is these days modified, slightly modified. Because the resin transfer molding process, this one, as you see, it need the mold, upper mold and lower mold, both of those. Okay? That means the upper mold and the lower mold, So it can be used to manufacture small size of parts only. It is not fit for the large size structure. But these days, the EV car, the electric vehicle, or aircraft, or the civil structure, basically a large part need to be processed. So this one, as it is difficult to use, and it's the productivity. Manufacturing rate is relatively slow. So, but this is good to study to understand for to get more the development of advanced ones based on this. So as you see, this process have the upper. This is upper mold and the lower mold, and the upper mold it must have an inlet for resin and the outlet. The outlet is for overflowing resin is coming out of during process. And the pump needed and the mixing chamber means this is the molten resin is here, and by pump it can be pressurized inject into this die, this mold. So after the cavity is filled by molten resin, and heat curing is needed. So of course, before the resin, the injection need to get a fiber preform inside. Okay, so that before the injecting resin, the fiber preform must be placed into the cavity. Okay, so that means this cavity is not empty ones. There is very complicated fabrics already inside. That means that the molten resin, it has a viscosity. So it is very difficult to infiltrate into it. Okay? So that means you need a high pressure to inject the molten the resin into. Okay? And once it's filled, then heat curing is needed. Okay? And after heat curing, it's ejected. So you can get one product here. Because this RTM is one of traditional technique already, and as I said, it is become the very basic method for advanced ones. So if you consider seriously the development of any composite system by yourself, in that case, strongly recommend you to build the RTM setup in your laboratory. It is not so expensive. It can be built very easily. Okay? So this is one of the built setup. So the power controller is even Arduino can do these days. So Arduino very cheap, and but this is not from Arduino, but you can use Arduino these days. And this is the mold. This is mold, as you can see, and the heating pipe is needed because you need heat treatment, right? And heating coil also needed. Right? It's very easy to install, and pressure bin also needed, and the pressure inlet. This is pressure inlet. Pressure is used to the push the molten resin inside. Right? For the resin, you need two different kinds of can. One is catalyst, another one is resin itself. So it should be mixed before injected into the cavity. So Schematically, you can summarize like this. Resin transfer mold process is if we think of full cycle from the raw material, so its layup is needed. This is kind of preform, right? So preform tool, this preform tool is fit into the mold. So cavity will capture the layup to fibers. So this is fiber form, the fiber preform. It's put into the cavity, and the resin infiltration is started, and the curing and opening for final product. That means in this case, it's just you can see the how the much time is needed to each step as a sample. So the transfer preform into mold 10 seconds in this case. This mold closing and the resin injection is 30 to 40 seconds. Curing is 120 to 9 or 9 seconds or something like that. Okay, so that means 120 seconds at 120 degree, and the 9 after that the 90 seconds at 130 degrees needed. This kind of schedule must be designed by yourself. So choose the time, heat treatment time, and the temperature. It's not just 2 steps. You can use 3 steps, 4 steps, and any kind of step is possible, according to your understanding, the fiber and the matrix system required. So it is the manufacturing the what to say. It's not the secret, but to that company it can be the very valuable information. Okay, because it decides the quality of their product. Okay? This is very important step, and from this step you can decide the quality of interface between fiber form and matrix. So this kind of schedule needs to be trial and error many times before set your process finally. And after curing, the injection, opening and the injection stage, about 10 seconds total, so 150 to 180. 180 second total time is needed. That means one cycle gets one product. That is productivity, and you can decide the price of the product. So this kind of full schedule means we say is a manufacturing process cycle. So that is RTM, and many of university laboratory have that kind of self-built designed RTM to make specimens for their new systems and get to know the effect of heat treatment schedules, so that they can write papers and can compare with their computations. So to develop your own product, it is not possible without understanding RTM process and how to calculate the process simulation, through simulation. So that kind of RTM is most limited the comment is it cannot make a large scale structure. It can only possible for small scale. So, and very slow, relatively slow cycle. So these days, this vacuum assistant RTM is most bestly required process. Even 2 or 3 years ago, I had participated in simulation for VARTM on the product by the Boeing, and because before VARTM, they usually use autoclave method to make their product, but it is very expensive process and the productivity is relatively low. So they wanted to get their product from their product by this VARTM, because this is very relatively cheap process, and each cycle, the production cycle is very short, and it's very easy to use for large scale structure. But there is only one problem. That problem is actually the dimension is very difficult. The final dimension is very difficult. So in order to make the finally accurate dimension, the company that provide the manufacture the product for Boeing or Airbus, they need to show their ability. They can get final accurate dimension through VARTM. At those days they claimed although you can make the product by your autoclave. In that case, I will not buy your product. It is the Boeing or Airbus claimed to the companies they manufacture their products. Why? Because in the end they need well-established the manufacturing process for their companies. So even though they can make the same product by a different method, in that case it cannot be standardized. So they need to have any standard method, common method from the companies that the manufacture Boeing or Airbus large-scale composite panels. So the VARTM is a mix two traditional methods. One is open mold, so hand layer you saw. Usually that kind of open mold method was used to build the hull of a ship. It's a very traditional method. So they have a very there is no limit to make the large scale hull of a ship by using open mold. So the large scale the product is possible by using the open mold. And another one is RTM. RTM is used. So both technique was confused into one. That is VARTM. So VARTM process means one-sided mold. There is no upper mold. Only lower mold is needed. That is open mold. And the dry fiber reinforcement, preform, is used. Okay? And that means it is very easy to be placed on the mold. And the vacuum bag will be used to seal the preform against the mold. That act like upper mold. The vacuum bag act like upper mold. And the resin injection under vacuum pressure That means atmospheric pressure will be acted like pressure air from pump. So pump is not needed because atmospheric pressure will act like that. And the resin injection under vacuum pressure and use of atmospheric pressure of compaction. That is that meaning. Okay. So this kind of RTM process needs to widely simulated by using computer. Okay. That technique one is crucial, needful one, and the practical technique training also very needed because to get actually to dimension as a final product, trial and error is very much needed because during a heat treatment process, the resin will be shrunken. That means the final dimension is not possible to estimate in advance. So after trying to manufacture practically, they can know how much that product will be shrunken. So by trial and error, they can negotiate to get accurate final dimension. And the VARTM combines following key benefits. So high part quality and repeatability, similar to RTM, and the flexibility and scalability, similar to hand layup, and the reduced volatile organic compound emission, and the cost effectiveness for large structure. So this large structure has emphasis for this process. Okay. But this VARTM also has some limitation because potential for air leakage and dry spot formation. Dry spot formation means dry spot, the preform, the fiber was not wet. In the case we after the ejected, we say it is dry spots found because there's no resin at all. Okay. And the limited control over fiber volume fraction. So fiber volume fraction cannot be increased to the limits. It cannot be because the pressure difference is just 1 atm, just 1 atm. Okay? And challenge in achieving uniform part thickness. It means there is no upper mold. It means between upper mold and the lower mold in case of RTM, it cannot be embodied here. That means the upper body is a little bit can be different because there is no upper mold. That means the product thickness can be varied. So that is a challenging point. So this is a kind of the schematic. So this kind of shape is VARTM. This pink line means vacuum back, and this blue one is a molten resin, and there is the resin inlet here. This is a resin outlet here, and so there's the vacuum pump is needed to make the vacuum condition inside the vacuum bag. Okay? So, and the outer vacuum bag, there is only the atmospheric pressure. So atmospheric pressure will the compact this the composite material structure. Okay? So that the molten resin should propagate, infiltrate like this kind of shape. Okay? This kind of shape is. So the process about the hand layup and the RTM and the autoclave, it does have some comparing points compared to VA RTM. So VA RTM has the advantages over hand layup. Its VA RTM is a more cleaner process and better part quality possible, and higher fiber volume fraction. But compared to hand layup, this VA RTM must have a higher initial tooling cost, and more complex setup is not possible for a VA RTM compared to hand layup. In the RTM case, over RTM, VA RTM has advantages over about lower tooling cost because it has no upper mold and the ability to produce a larger part. And more flexible mold design is possible because there is no upper mold. And the limitation compared to RTM is a lower injection pressure because just one ATM is used, and the potential for dry spot because this can be happened due to small compaction pressure. And over autoclave, so VA RTM has advantages, the lower equipment cost. So autoclave is very expensive equipment. And the ability to produce a larger part. Autoclave also used for curing larger part. But the VA RTM case is much cheaper, or facility can be used for it. And the limitation of autoclave is a VA RTM is a low maximum fiber volume fraction because compaction pressure is low, and the potential for thickness variation this is inherent weakness. Okay? So VA RTM can be said is one of the most needful technique these days. So the large scale composite material, the manufacturing company is use either filament winding or VA RTM. So that is the case of large structure or composite panel manufacturers. So the VA RTM, if you understand the fundamentals of VA RTM, in that case you can understand the better control and process optimization. And as a result, you can improve part quality and fewer manufacturing defects because differently from RTM or hand layer or autoclave, this VA RTM has many variations, thickness variation or dimensioning, the variation, something like this. So that means more trial and error is needed without good experience in advance or the simulation. So if you can use a simulation, that means you can know the rough optimization point in advance. So from that spot, you can reduce the number of trial and error of VA RTM practice. Right? That means it can save your time and it can save your money. Right? So the key physical phenomena for VA RTM process is resin flow phenomena and fiber preform compaction and resin viscosity and the composite curing behavior. These four subjects should be understood to use VA RTM manufacturing technique for your product. Okay? So resin flow phenomena, that is about fluid flow through porous medium. And the fiber preform compaction is about affecting the final part quality and the fiber volume fraction. And resin viscosity is about affecting flow behavior and the filling time. And the composite curing behavior is complex heat transfer and chemical reaction. So these four subjects should be calculated in advance by using computer. So, I just give very basic fundamental equation. It is not. I have an intention you have to study this equation, but there are some commercial packages to simulate this kind of things. But behind that computer the graphic user interface, this kind of equations are included. So you can to check any kind of documentation if you wanted to have any intention to study more deeply. It's a 1/4 subjects. Right? So for example, resin flow phenomena. So just two kind of equation the related theories needed. One is Darcy law. We say Darcy law is a kind of a flow into porous medium. Okay? So these are related the equation, and also continuity equation is needed to consider. And VRTM, so in the viewpoint of resin flow, so it has key aspect is through thickness flow, and flow tracking, and the dual or scale flow. These three minor subjects included. The through thickness flow is the primary direction of resin flow is through the thickness of the preform, and facilitated by flow distribution medium. So you can see the later about that. And follow tracking means the resin may flow faster along edge or channel, resulting in uneven filling. And the dual scale flow means the resin flow occur between fiber bundle and within fiber bundles. That means between fiber bundles means we say it is a macro flow, and within fiber bundles microflow. So one bundle means 1K, 2K, or 10K. We say like that. 1K means one bundle. 1K bundle means 1,000 fiber. So the binding in one bundle. So 12K means one. So 12K means so 12,000 fibers are bundled. So those kind of terminologies used. And about fiber preform compaction, so we use two different models. So this is very famous models in this field. So Gutovsky model and these two models is usually used for computational programming inside. Okay? So effect of compaction is concerned about the preform thickness, porosity, and permeability. Okay? And the resin viscosity. The resin viscosity we use this kind of model. And this resin viscosity is considered temperature control and part life of a resin system, and viscosity change during cure. And the curing behavior of composite material, so we are using this energy balance equation and kinetics and this curing. So this kind of equations the programmed into commercial packaging. So you can use chemical reaction or any heat treatment or fluid flow, viscous flow, those kind of things you don't need to understand in detail, but those kind of things are already programmed into commercial packages. So that if you just understand the stories of each subject, then it can make you use more usefully the commercialized packaging. Yes. So this is composite pure vacuum systems components. So there are many terminologies here. So this kinds of terminology is needed to you understand, because to use the commercial package, they ask that kind of terminology as a parameter. So you should set your model for a product. Okay? And this is kind of the photo for the radio controlled aircraft fuselage, the open mode shape. This looks very messy, not so neat like schematic, but this kind of open mode hand up is very, it looks like the VRTM, so low mode. So VM RTM process setup and processor can be the simplified like this. So air compressor is needed, and electric scale is needed, vacuum pump needed, gas container needed. So these four the equipment around the manufacturing bed. The inside the bed, there is a lower mold here, and there are many fiber preforms here, and there's this green one means need fill ply. This is one of element used for VRTM, and this vacuum bag. This vacuum bag is pink color, and the sealant tape is this is used as a bumper, right? And the preform, the carbon fiber is preform and valve. So you can understand what kind of measurements in this. Pressure is monitored, okay? And temperature should be monitored, and this valve will be controlled from outside. Okay? So this glass window is needed because you need to look into the product during process, during manufacturing. So the simulation means all of the materials included inside the manufacturing bed is needed to include. So vacuum bag, fill ply, this tape, pipeline, not this pipeline, the carbon fiber. Those kind of mechanical properties, depending on temperature, should be known in advance. So those kind of temperature dependent mechanical properties can be obtained from supply. But if you don't know what kind of mechanical property needed, in the case you cannot ask them what you need. So if you have some special composite system in mind, then you need to focus to get what kind of things with mechanical properties you need, something like that. Then the parameters will be supplied from outside if you ask. Okay? So otherwise, you must use kind of default parameter properties provided by computer package company, but it is not accurate. It is not accurate. It cannot be used for evaluating your manufacturing process. It cannot. So it is just for exercise. So meaningless. So you must get real properties to use that commercial process. So, and the key consideration of VRTM, so in summary, is a preform compaction and the flow front control and the temperature management, vacuum integrity, resin bleeding, post-cure. Those kind of consideration must be concerned. Okay? So each of those, I believe you can quickly understand what those are, right? So preform compaction is preform compaction means that preform you have a stack of carbon fiber, for example. It needs to be preformed. But if you use too much the strong compaction pressure, that means that preform will get pre-damaged. It is not wanted, right? So, if, for example, if you give too much the compression, then locally there will be locally buckling can be found. And that buckled mostly can be recovered after removal of that convection pressure, but during buckling, it can live in permanent breakage in fibers. So it will be the micro defect after manufacturing as it is. So don't neglect the optimal compaction pressure. And the flow front control means it monitor resin flow front and adjust injection as needed to prevent dry spots or racing tracking. It means resin flow. Resin must be flow from the one side. From our previous schematic, it must start from left upper corner. So that point is a starting point. And during the resin infiltration, that the front, the flow front will move right and downward. So if the speed is not well controlled, then it's too slow or too fast. In the case, there will be some unfilled space, or according to that space size is macro size void or micro size air trap will be found. So it will be the final defect. So it cannot be used as product. So that is flow front control. And the temperature management is resin viscosity must be well taken care of. So viscosity, liquid viscosity severely depending on temperature. So if manufacturing temperature is different from local to local, that means each part of viscosity flow characteristic will be different. That means filling rate will be different. That means it's the filling status will be different. That means your final product will have inhomogeneous inhomogeneous properties will be displayed. So it is uneven property local to local. So it cannot be used. So according to the local temperature, you should try to keep the temperature as constant. So, if it is very small product, then it's very simple to keep the constant temperature. But why we need VARTM? Because these days most of composite structure has a large scale. It's 3 meter or 5 meter long, or sometimes 10 meter or larger. Then it's a very long distance in manufacturing process. So it is not inside the insulated the space. It is open space. So how you can keep the temperature constant? It's very difficult. So UV is not enough to use. I mean any kind of technique to keep temperature, heating or cooling is needed to keep this optimal condition. And vacuum integrity, continuously monitor vacuum pressure and address any leak immediately. That means vacuum pressure is so there's a compaction. The compaction pressure is only atm, 1 atm. So if inside the vacuum is not complete, that means compaction pressure will be diminished. So it will be the different situation we expect. And the resin bleeding. So resin bleeding is some extra resin should the leak out, bleed out. Otherwise, it will make the epoxy rich zones of the inside. So it will give the very weak structural zone. Yes, so it must be careful. And the post-cure is depending on the resin system. Post-cure cycle is needed to achieve optimal mechanical properties. So mechanical properties decided finally after heat treatment. So depending on the characteristic of based on the same the material combination, the final mechanical properties are very different. So that is about VARTM. So now we can say about just conceptually vacuum assisted composite manufacturing techniques. This VARTM is one of those. Right? So this vacuum assisted composite manufacturing. So first step is preparation. Now you understand what is preparation in this place. Okay? So layup, okay? Dry fiber layup, because need to make a preform. Okay? That is first stage. And bagging. Bagging means vacuum bag bagging. Right? It's needed for this kind of vacuum assisted one. So bagging is needed to sealing the layup with a vacuum bag, and the tacky tape is needed. And the installation of a resin inlet and the vacuum port. Okay. Now you easily understand why there is resin inlet is needed and the vacuum port needed. It's a vacuum assisted manufacturing technique. It's mandatory needed, right? It's very basic. And the infusion is need resin into the preform. So infusion means drawing resin through layup using vacuum pressure, and then ensuring complete without fibers. And the last stage is curing. Curing is heat treatment. Okay. So allowing resin to cure on the vacuum, the demolding and the post-curing is necessary. that is a general stages needed for vacuum-assisted composite manufacturing. And this kind of techniques advantage is it can enjoy, it can provide higher quality as a result. So reduced and void air traps and improved fiber to resin ratio, the enhanced mechanical property and the surface finish will be possible. And the cost effectiveness, because it has no upper mold. And so that means the pump is not needed. So, differently from the RTM. So lower material waste and labor cost. Of course, it can be obtained and suitable for producing large and complex parts efficiently. So it's advantage from hand layup and the RTM. So both advantages can be used for the vacuum-assisted composite manufacturing. The versatility is compatible with various resin systems and reinforcement adaptable to different part size geometry. Is very fit to those kind of structure. So vacuum-assisted process has key components. So for as a manufacturing method is vacuum pump. So vacuum is mandatory needed, right? And flow media. Flow media facilitate even resin distribution across the part. Ensure complete fiber weight. This flow media means it is a kind of the kind of molten resin flow or channel kind of. It can easily transport a molten resin over the preform, so it can accelerate the molten resin transport. And the resin trap prevents excess resin from entering the vacuum pump. So protect equipment from damage. Vacuum bag is needed. Okay. And the mold and layup preparing. So mold preparation for this manufacturing technique is mold preparation must clean. This mold is lower mold because there is no upper mold. So clean and apply release agent. Release agent is after the finish, after curing finish, it should be easily ejected. So that need release agent is needed to dot over mold. The ensure smooth surface for quality part finish, because mold surface condition can decide the surface of a product. And the fiber placement is this place the preform on the lower mold part. So cut and position reinforcement of fabric, and follow designed apply the schedule for optimal strength. Okay, about preform preparation. And then auxiliary materials needed, peel ply, flow media, and breather. So over those kind of the sheets should be placed over preform to help the resin flow. And the bagging and the sealing is very important, because this is a vacuum assistant. So if there is the bad sealing, in the case the process of fully the failed. Right? So vacuum bag placement is the drag back over layup and avoid the wrinkle to prevent resin leach area. And the sealing technique is advised, and the port installation and the leak check is mandatory before starting this process. Okay? And vacuum and resin infusion. There's a vacuum application and the resin preparation, infusion start, and the flow monitoring. Each of the contents should be applied for this manufacturing technique, especially with very special caution, because vacuum application indicates gradually increase vacuum pressure, monitor for any back movement or distortion. So because to avoid any damage or unwanted shape from vacuum pack. And the resin preparation is a mix of resin and hardener thoroughly. The well mixed is needed. Okay? And degas if necessary to remove air bubbles. Okay? So the reason this kind of the application cautions listed, because in practice this kind of application frequently leave many damages or defects just after manufacturing. So each application part must be checked if you train or exercise this RTM like a manufacturing technique. So, and infusion start. So open resin inlet valve slowly. So observe resin flow front for even distance. This is very common sense, but we don't know how slowly the valve should be open, it closes, something like that. But that means any kind of the abrupt application of open or close or pressurization or vacuuming will make a permanent damage on your product after executed. So those kind of things is very common sense but it must be cautioned. And the flow monitoring is adjust the inlet pressure as needed. That means flow must be fit must be appropriate to the make preform fibers wet completely. If it is unwet partially, that means the total structure will be the failed output. Means this way RTM is usually used for large scale structure. So that means one failure of manufacturing, that means big time consuming and big cost lost must be expected. So you should very carefully the practice this kind of things. And curing and composite part, initial cure, temperature lamp, cure, hold, cool down. Okay? So you can read this slide after this, because you can get I guess download this slide for use. From this slide you can get more documentation with the same terminal, something like that. But this can be used as just a note for you. Right? And the consideration for part design optimization, geometry, resin flow, ply schedule, and cure profile, and the troubleshooting common issue. The dry spot, resin leach area, vacuum leak, premature gelation. This kind of issue is very common. Commonly encountered issue during vacuum assisted composite manufacturing. So if you got a dry spot, then the common cause of dry spot is poor resin flow. So how to solve that problem is adjust the flow media layout. And the resin rich area found, then it means maybe excessive resin pooling. So to resolve this problem, so optimize the vacuum pressure. It must be controlled. And the vacuum leaks issue, the improper sealing is the cause. So double check back-end connection. And premature gelation found, then incorrect mix ratio caused it, and solution is verify resin and hardener measurements. Okay? Those kind of the common the issues can be treated. And that is about vacuum assisted composite manufacturing technique. So it is not automated. It is not automated. So VRTM also to preparation of manufacturing process, all of steps you should prepare by yourself. That means much manual job needed. So it cannot be the fully automated. So so that's why still it is not fit for mass production part. But very special and a small number of productions, those kind of case it can be advised. But recently, so most of the applications needed to be lightweighted, but keeping its structural strength kept. So it is very difficult to be achieved based on conventional materials. So although composite material is very expensive, many cases the using composite materials is the only one solution to get a final product, to meet the requirement. That means we must overcome the cost issue. Okay? So it is not possible for all kinds of composite system, but if possible, we want to replace manual work by machine, automatic machine. So these days, the advent of robotics development. So we can build very sophisticated manufacturing robots even for composite materials. So this kind of manufacturing machine for composite material manufacturing, it is also initial stage, not a fully developed market yet. That means there are possible automatic machine for composite materials, but still very, very expensive. So small and medium company cannot use it. It's impossible. Only very limited number of the multinational company can use it if needed. Okay. So, but it's very surprising for me to see so many automated automated composite material manufacturing machine is introduced in the market very rapidly. So I think maybe in India, I think because in India there is, I think most of, for example, most of manufacturers in automotives, for example, can be found in India. And for automotive makers, this kind of composite material component is just beginning stage to be introduced. And what it is to the automotive manufacturer, I think mass production is their basic principle, differently from the the airplane manufacturers. That means automated machine for composite material will be very much needful, like India or China, something like that. So if you can combine the recent robotics and automated machine for composite material, then you can contribute greatly to automotive parts industries and for other application manufacturing companies. So, in that sense, it is meaningful to introduce about automated tape laying machine for composite material first. So that's why I chose this topic as one of the subjects today. So there are the ATLs. ATL is automated tape laying. Here is a tape means a composite tape, that film. Kind of prepreg. So definition, the ATL is computer-controlled process for laying pigmented composite tapes. And it precisely places tapes on a mold surface to create complex structure. So placing films, fiber preforms on mold surface was traditionally man's manual work. But now it is tried by using automatic machine. That is ATL. Its efficiency is significantly reduce labor and improve consistency, because it is that work is done by automatic machine. So it should be very accurate compared to humans' manual work. Okay? So its consistency is greatly improved by using ATL. And it is very ideal for large and relatively flat or slightly curved components. This is the limitation of this machine at this time. Because if it has very complicated curved surface, that means automation is very difficult, not easy. So it is not overcome yet. But if it is very flat and very gradual or curved one, then it can be work done by automatic machine. So that means these days ATL is a very the flat-like structure only, not the so curved one, complicated one. And the precision, the ATL machine's precision is it can achieve tighter tolerance because it is machine, right? And the excellent fiber alignment. Of course, it can be expected. crucial for aerospace application requiring high structural integrity, because this is not possible for automotive part yet, because automotive part is small and the surface, the geometry very complicated, so it is not possible. But for airplane, its body is very large cylinder, or its wings are very flat, so it's very useful. But that is dilemma for this machine, because how many airplanes will be manufactured 1 year? It's a very small number. But this ATL machine is very, very expensive. You can see this right-hand side, this one is one of ATLs. These are also ATL machines. So this is not millions or million dollars, not $1 million. It's tens or hundreds of $1 million. So who can install this kind of machine into the industry to manufacture small number of parts? Okay. Anyway, so this is the already found on the market. Okay. It has very flat mold and very very large radius curvature and so on, right? And the ATL process flow is very similar to handle layup. And the first, material preparation by machine. Okay. So the machine can pre-impregnated tape can be loaded onto the ATL machine automatically, and the material is carefully handled to maintain quality, of course. And the tape placement, the machine had precisely laid tape onto the mold surface, and it follow a pre-programmed path for accurate placement. And the compaction is it use roller, that robot hand. The roller on the robot hand applies pressure to ensure proper adhesion. In hand layup, that kind of plate, and we use the hand roller. But now that the robot hand use the big roller. So its compaction pressure is very, very accurate. Right? So this compaction, so as a result of this compaction now, it can remove air pocket. And the surface ensure the good quality consolidation. So, and the cutting and restart is very quick and accurate. The tape should be cut. In the hand layup, we use knife by manual. So, but machine use is the machine knife, machine seizure sometimes, and at the end of each pass, and the machine then repositions for the next layer. It's automatic. So, key component of ATL system is a robot arm, and tape feeding system, and the cutting mechanism, and the control system. So all of these kind of things can be possible for only these days, not 10 years ago, 20 years ago. And as I said, still it has big limitation. Only the flat surface only. But maybe the robotics, maybe it can be introduced on commercial market sooner or later after new robotic industrial period will become. So every expert expect like that. Because these days there is only small number of industrial robots can be possible, scalar robot, something like that. But humanoid type robot is about to be on the market now in 2 years. That means in 2 or 3 years, the humanoid type robots can be used for this kind of automatic composite material manufacturing machine. In the case, very complicated the surface can be treated. And then what you can expect, then composite component parts will be commonly used for every kind of machine, automotives, mobilities, structures. So it will be very difficult, different. The period will come, I think. So robotic arm has provide precise movement and the positioning of tape-laying head. So these days, only very simple work is replaced by this robot arm. In the case of composite material manufacturing area, and the tape feeding system is easily can be expected. And the cutting mechanism and the control system. So even this kind of the simple work, that ATL is very expensive and less the complicated work compared to human hand job. So, this is very open field, I think. So material type for ATL is used basically carbon fiber prepreg, the glass fiber prepreg, and the aramid fiber of prepreg. Okay? So now you easily know the carbon fiber and the glass fiber, aramid fiber, the differences between them. Right? And each advantage also you now the well grasping. Right? So advantage is a carbon fiber, high strength, lightweight. Glass fiber cost is relatively low, the cost effective, but and very good the thermal insulation and electrical insulation. And aramid fiber is impact resistant exclusively, right? And the vibration and the damping characteristic. So this kind of fibers we reviewed in the lesson. So those kind of fiber is very commonly used for advanced composite. So even for ATL, so carbon fiber prepreg, glass fiber prepreg, aramid fiber prepreg is used for carbon fiber case, aerospace structure, high performance automotive. And the glass fiber is marine or wind energy blades. And aramid fiber is ballast protection aerospace interiors. So glass fiber prepreg is relatively heavy. It has the low strength, the low specific weight. Comparatively, it used for ground structure or the ocean structure. So optimizing ATL parameters as a layup speed and the compaction pressure and the temperature control, tape tension is the same as the parameters you have seen in the VRTM or hand layup process. So applying to the same, right? So this can be more accurately controllable through ATM. And the quality control was very automatic in-process monitoring is possible through various sensors, and non-destructive testing is on-site is possible, and the dimensional accuracy is possible. And the sustainability and the future trend in ATL is a recycled material, AI integration, multi-material layup is expected, because all of those ones is focused on the eco-friendly environment requirement from society, and if we adopt AI integration together with ATL, that means more sophisticated, complex surface can be handled. So it's a very understandable trend. That means that motion will be very the interdisciplinary fusion area. And the introduction to the automated fiber placement. So this is also the similar but a little bit different automatic machine. So fiber placement, automated process, complex geometry, this can be used by automation. So this is a kind of the AFP, the machines. So this is some of those are just for fiber placement only. So it can work on a little bit more complicated surface, differently from the ATL. And the key component of AFP system of fiber delivery and placement head motion system is similar to ATL. And advantage over AFP over manual layup, enhanced precision can be enjoyed, and increased productivity, and reduced waste, and improved consistency. It's similar to the ATL, right? And the material used AFP manufacturing is carbon fiber used, glass fiber used, thermoplastic, and prepreg tapes. All of those can be possible for existing machines. And the layup strategy and optimization, fiber orientation, layup sequence, compaction force can be controlled automatically by the AFP machine. So inspection and quality control in AFP in situ monitoring is possible, and dimensional inspection also possible. Destructive testing is on-site possible. Right? And the challenge and the limitation of AFP is complex geometry. So still it has some limitation, like ATL, and the defect avoidance and the material limitation and the high initial cost. Still, the said their limitations. And the AFP technology, the future trend is intelligent automation also being tried, and the digital twin is also used together, and sustainable materials are required. So among that, digital twins means digital twin is creating virtual simulation of AFP process to prevent defect before production. That means currently the machine is just controlled by a program, but that means a computational model will be collaborating with this machine. In the case, before operating this machine, the digital twin means a computer model used to predict the result of manufacturing in advance. So before trial, some kind of parameters can be controlled in advance. So it can save time and money. Right? So application in composite manufacturing is aerospace, automotive, wind energy, and sports equipment already. Yeah. So this is about the manufacturing techniques. So this is just a part of all manufacturing methods because all of those cannot be discussed here. But today I focused just three the crucial ones. One is RTM, another one is VA RTM, the last one is fully automated machines, three of those. Those are the currently commonly used ones. Have any question about this? It's a little bit cold here. Okay. So interesting one is so if you understand the composite system and composite system first, then after that you got to start thinking how it can be manufactured, how it can be made. The manufacture means like some industrial the terminology, but you can think just this small patch of that composite system. How I can make this composite. So you can try by yourself. You can use oven, electrical oven, small electrical oven to heat treatment by yourself. You can check 2 or 3 cases sufficient. Then you gotta know what kind of different result can be obtained after this heat treatment. That one. Okay. So overall temperature can be known, although it is not accurate. It can be checked from the documentation already. So once you can experience any kind of composite manufacturing by yourself, in that case, it is a very good start point to design your own machine. And it is very good. In that case, it can be named separately. So you can think how many different manufacturing methods can be found these days. So once you know the other patented manufacturing technique, understand those, it is nothing. It's nothing. It's very natural. If it was your case, you could do like that also, but it's already patented. But there are so many different ways. It's open ways to develop new manufacturing technique by yourself. But it must be rooted on special composite system. Because different composite system require different manufacturing technique. So the most important thing is to understand the composite material system. Before that, where you want to apply that system. The part structure you want to have. To find that part is first mission. After that, rather than just a traditional material, if you want to make it by your composite material, then you can check what the system is, possible fiber, sometimes carbon fiber, rather than you can use your hair. Can you say? It's very nice fiber. It's very nice fiber. It's just 50 micron in diameter. Okay. So it's so very nice. Maybe you have a very smooth hair, then your hair diameter may be less than 30 micron. It is very expensive advanced fiber already. That's natural fiber. natural fiber. So you can, don't use of your friend's hair, use your hair. So it's very interesting. Interesting thing if you try like that. You can be the composite material export sooner or later. Okay. Yeah.
Automated tape-laying method, is it possible to achieve higher diversion percentage, higher volume fraction?
Yes. The ATL or those kind of machines can achieve the highest the volume fraction. But the VARTM, it's not possible. VARTM or hand layup is not possible. But RTM is possible. So it is because compaction pressure and the temperature, temperature control is the issue, key issue to achieve a higher volume fraction. Because it must be well compact, and the resin should be well molten, and so that all of the fiber must be completely wet. But by using VARTM or hand layup, it is not possible. It has a limitation. But if it is through the machine, automated machine, it is, you can control every parameter very precisely.
And what about the bonding between the layers? So we are using ATL or AFP?
So adhesive or the polymer can be used. So you mean the between ply? Between ply. It's a conventional adhesive. So you know the paste. So not the paper paste. Okay? There are many industrial paste. It can be used.
And we are discussing about the thermoset regimes.
Thermosetting?
Manufacturing of composite using thermoset.
Yeah, thermoset is mostly used. Yeah.
What about thermoplastic?
Thermoplastic also can be used, but the thermoplastic case its use is mostly low temperature, not the high temperature. So thermosetting is a little bit more solid at elevated temperature, even polymer, because it's cross-linked. So mostly epoxy resin is used, the polyester is used. Not vinyl is not used for, vinyl is thermoplastic, right? Because it is not rarely used for automated machine resin. So mostly.
Can we use these methods for the thermoplastic as well?
I think so. Why not? Why you do you think thermoplastic is difficult to be used by?
Because in general we used to get the thermoplastic in the solid form, like the granules or powder form. So it will be difficult to.
But I think if that thermoplastic is made as a layer form, as a tape shape, for example. Not you just think about plastic molding. So in the case of powder is the material, but if it is made like a tape, pre-framed shape, in the case it can be used for ATM machines. In the sense. So I mean the intermediate level of thermoplastic, not the raw material level thermoplastic. It is powder, it's not used for the automatic machines. Because it is kind of plastic mold, plastic injection process. Even composite, if you wanted to use those kind of things, you can do. But in the case, there are many void trapped inside, so no one wants to use like that because there are many fiber preform inside, and the powder must be molted into that cavity. It's very difficult to get fiber wet. That means after there's many void, so the product will not be good. In the sense, it's not good. So